Okay. No, I just briefly repeat what I just said. If you are right there. And we got a strong wind. Now, I don't know which way the wind is blowing. Because I don't feel it right here. I've got it shielded somehow, but I know there's a strong vector field there. It represents the velocity of the wind particle, whatever. Wind particle, air particles. Molecules. Atoms. Okay. If I throw this light piece of paper, I don't want to hit you. This way, best place to aim, then, assuming that I'm accurate, is it's right at your head. Because I know the wind is going to carry it that way or that way, and you're safe. Now, the rest of you over there are in grave danger. Because you don't want to get hit by this thing. It looks harmless, but you don't know. Okay. Okay, so there's a vector field out there. It's going to deflect with half this thing. Now, if the thing is charged, and let's say I'm shooting it out of a little air gun, okay? So that handling it, I don't discharge it, okay? It's charged, and there's a magnetic field in here. Well, the same principle, except the way the velocity changes is somewhat different. Okay, if the magnetic field is across this way, depending on the charge of this thing, if I throw it straight at you, as we're going to see when I give you the rule, and what I said before is wrong. If the magnetic field is in your direction, I'm going to hit you. Okay. Because of the rule. If the magnetic field is down and this thing is positively charged, it's going to curve off that way. Mission. If it's up, that thing's positively charged, it's curve off that way. Of course, it's negatively charged, up negatively charged, and curve this way, down negatively charged. Or not, it'll curve that way. Okay. So the rule is pretty simple. The force is QV cross V, V being the velocity, V being the magnetic field. Okay, so I'm going to ask you to reason this out rather than telling you, because you learn it better if you reason it out. Or if you fail to reason it out, at least try to reason it out, you're still going to understand it better when I tell you. I'm going to give you a couple of minutes to answer a couple of questions. So what should be the units of V? And then what should be the direction of F if V is in the negative Y direction? And magnetic fields in the negative X direction. Okay. Now there's a way that you can do this. You just say let V equal scalar V times the negative J vector, okay? And let V be scalar V multiplied by the negative I vector and do the cross product, right? Don't even do that, but don't. Just use your right hand and figure out what the direction is. Okay? Now, then I guess I should say, let's let Q be negative as well. Okay, I didn't look too closely, but it looks like everybody did real well with the units. Either got it or had something that with one simple step would have it. So everybody's thinking that. Okay, so negative Y directions there. That's your velocity. Okay. And fields in the negative X direction, that's this way, right? Okay, so we put our fingers there, turn our hands and turn the fingers toward the negative X direction, and you get it down, right? Now that's your V cross B. You got to multiply that by Q, which is negative. It's up. Okay. Makes sense. All right, well. Pretty simple, right? Very simple rule, no constants. Things just okie dokie. I don't even know what that was. That was a dated expression when I was born. Okay, well, that's it. That's magnetism. You got it. Well, no, there's. Okay, well, if you got a wire with charge drifting, if charge is drifting in the positive direction, you got a bunch of charges, all with some small velocity, usually, you know, in the order of millimeters per second, even fractions of millimeters per second. Depending how much current you got and how many charge carriers you got and how big the wire is. Okay. So what you would do is take the average velocity of an electron or the charge carrier. It could be in an ionized gas or something. You have ions in both directions. But you take the average velocity of the charge carrier, multiply by the number of charge carriers. Okay. And cross that. Okay, so drift velocity does have vector nature. It's in the direction of the wire. And these things are drifting in the direction of the wire. So it says vector. But let's not call that V, because that actually tends to confuse the solid V drift. Then without developing it just yet, another simple step. You get the current times the length. Cross. Okay, they're relating this expression to current and length. Take a couple of pictures and a couple of steps, so we'll do that. Right now, this is just another form of this. Okay. L. So it's a vector of length L. In direction of two charge times the drift velocity. So this is the force. Like L of a current. Okay. So you got a wire. 10 centimeters long. You multiply 10 centimeters by the current. And then cross that with the magnetic field and you get the force. Okay. So well, okay. So my ultimate question is, I've got a current in this loop of wire, assume it's a cylinder. Okay. What's the net torque in this thing? There's going to be a torque. Now, circles a little more complicated, involves integral. So I'm gonna make this into a square. I'll get choked up when I talk about this. Okay. Make this into a square or a rectangle. Okay. And let's say we've got a magnetic field, could be in this direction, parallel to the loop, or this direction, of course, but that would be kind of the same as it's computational, or this direction. Okay, so either parallel to the loop or perpendicular to the loop. I'm going to say each side of this, we'll make it a square. Each side of it is L. And we got current I. Okay, and just so we have a point of reference. It's in the XY plane. And what's the force on each? For B due to BI. For BI, of course, I is going to be parallel to the plane of the loop. Okay. And due to BK. Which is going to be perpendicular. You know, imagine this thing is flat. And usual orientation we visualize. Okay. So what's the force on each side of this thing? Okay, now, what most people did was they wrote this out symbolically. Worked it out. I think correctly. One person had this thing in the XZ plane, and that's fine. You get the same idea, but I'm gonna explain it as black plane. Yeah, I think maybe that person changed. Okay, so here's our loop. Oh, man. It was too big. Okay, well, we see. This is a more or less square. Okay, so we got a current going from us here, up here, here, and here, right? Current is I. L is the length. The length, I think, is 2 feet, which is about 60 centimeters. Okay. So we got 60 centimeters here. Let's take this part of the loop. Okay, now X, Y, Z as usual. So this is in the negative Y direction. Negative X direction. Okay. So in the negative X direction, we have current I. Okay. So the current is negative I. Negative. That was probably bad something to start with. The negative I, capital I times the I factor. Okay. Now we're doing. Actually, the way I just explained that isn't, I mean, it's totally consistent with this, but it's not the way you're probably going to look at it. And L is negative 60 centimeters times I, which is just negative Li. Okay, L times the I factor. So if you replace that with scalar L times the I vector, then what's B? Well, first B is BI. Okay, so B is in this direction. And your current is in this direction. Okay. So your IL is in the direction of your current. So what's the direction of your force? Right hand rule. Well, these vectors are parallel, you get 0. Okay. You try to turn this vector into this vector. Okay. And you know, of course, the cross product is magnitude of this times magnitude of that times the side of the angle between them, and the angle between them is pi, or 180 degrees. Go back to circular model, just visualize it. Projection onto the y-axis, circular model gives you 0. Okay, you should be real familiar with that. And you should think that whatever you want to find the sine or cosine of a multiple of 90 degrees. Otherwise, I can memorize a number and it gets confusing. Okay, well, anyhow. So we've settled that, and the same thing is going to happen. Okay, carpal tunnel doesn't want to do what? Okay. This direction is again parallel to the magnetic field and in the same direction. That doesn't matter. Okay. Now we go across this side. So we got L times negative I. Okay. Negative J. Okay, L times negative J. So we're going to have I scalar L J vector cross V I, right? Vectors J cross I. Then we have ILV times J cross I. Okay. Now that's what the symbols tell us. What's our intuition? Well, yes. Okay. Currents in this direction, magnetic fields in the positive X direction. It'll be K. It'll be, so we're gonna get the force in this direction, the magnitude's still gonna be ILB. So on this side, we get a positive, and on that side, we're gonna have a positive J crossed with I, negative J cross I is gonna give us a downward force. And what's gonna happen then is this side is gonna be pushed upward, and this side is pushed downward, giving us a torque. And then to rotate this thing. And well, no, but then so the symbols ought to lead you to a visualization. And ultimately, you're not going to really need to think in terms of the symbols, although you want to write them down, you think in terms of directions and cross products, and then you get more used to cross products. You're going to get more important by the end of the term and whatever other calculus too. Okay. Okay, so let's just look. Okay, let's take this down. Well, if this is in the XY plane, so your square is here. If you focus this here. IL would be ILJ. So that then we're going to use the BI. Using those constants, we get ILB. And then J cross I. Okay. J. Okay, what I just gestured. Assume different, actually what I just gestured was on this side. The first one I did, the side that was over here, to correspond to this because of the way the X and Y. Okay. So anyhow, so J cross I is negative J. So negative ILBK. And that's the force on the other side. Force on this side is, well, the current in this side is negative I L times I vector. Around the loop in this direction. And I guess I could draw the IL function. There's the IL force. Now, here it is. This side. And now I should number these sides to keep it straight, but I'm going to just call it. And I'll do this one in green. I'll write it as IL times negative I, to be really explicit. It's zero because I cross I is zero. Then on this side, we have negative ILJ. So that ILB. Makes sense? And then four side is zero. Okay. Now what's the torque? This force. Okay. This side is being pushed down. This is being pulled up. You can see coming out this way, right? It's gonna be a torque like this. About whatever. Okay. Now you calculate the torque about any point. You calculate it about the y-axis. And you're gonna multiply the moment arm, which is just L times your ILB here. It's gonna be the negative direction, okay? Well, the moment arm is a vector from here to here, so the moment arm is Li. You multiply that by negative ILJ. What's negative I cross J? What's the negative? Okay, shouldn't be. I cross K, so negative I cross K. Okay. Which is going to be J direction, so it's a torque about the y-axis. So I can just say. About torque. This is important. Our generators. Okay. Well, about the flux and about this, but so we get the idea. The torque, it's why DC generator, where you put a commutator with this, keep reversing polarity every 180 degrees. And that's a DC motor, and you can read about that. Torque about the y-axis. Cross out. The R vector is okay. The torque on the side at x equals L. This side is at x equals L. Okay. Then the torque is R cross F, it's Li cross negative ILBK. R cross K is in the negative direction. So I cross K is in the negative J direction, okay? I cross K is negative J. And we got a negative, so it's IL squared B. Okay. That's torque on this side. There's no force on this side or this side. No torque due to those forces. And moment arm on this side is zero because you're on the y-axis. Okay. Now, if you were to calculate it about this axis, Your moment arm would be negative L times J. And your force would be positive ILVK, and you would get the same thing. Calculate the torque about the center. Well, you get half of what you got here. And you get half of what you get here, which is equal to what you got here. It comes out the same. Do it about any axis of the universe, parallel to the y-axis. You still get the same torque. And it's worth working that out. Practically, if you're doing a motor, first place, you probably use a circle. Because it's really easy to form circles by wrapping things. Squares, a little tougher. They're not as convenient. But sometimes you use them. Can I say that like I know? I think so. If it's a circle, then you got to do an area. Okay. And we'll do that. But right now, let's just understand this. Okay. So that's a really important application of this rule. Now, let me check something. Okay, there are insights to be gained here. You don't get a torque about any axis if you have the VK. Okay, work that out. Use your right hand. Figure out what the forces are on the four sides. And what I just said was right at all. The force in this doesn't have a root. That didn't seem right when I'm saying. You're going to have a J cross K for this one. J cross K is I, and I is this way. Okay. Use my three-dimensional figure here. Is what I'm doing here. Yeah, what that is I tend to push this side this way. It's got to be perpendicular, and I was getting something parallel to the force, which was just ridiculous because it wasn't oriented in space. Okay, I knew that. Yeah. Over here, you get the opposite. It tends to push it this way. It's tending to stretch this thing in this direction. Okay, and the force is here tending to do the same thing. You need to work that out. Well, I didn't say what I said before on the recording. I had it recorded. I was still there. Okay, I want to talk about flux. It was. So let's say this is the XY plane. And you've got a magnetic field. Let's say you do have the BK. So let's say this is negative BK. I haven't talked that much about orientation of surfaces yet in full verbal calculus, so I'm just going to be a little bit fuzzy about what we're doing. You have the counterclockwise direction is generally regarded as positive direction. Okay. And the counterclockwise direction, the right-hand rule gives you a normal that's in this direction. This normal force that a normal vector is a vector perpendicular, and of course you know this from multiverbal calculus. But if anybody's listening that doesn't have multiverbal calculus, just a vector perpendicular to this surface. Okay. Surface enclosed by this rectangle. or area, could be a circle, could be anything. Okay. And such that if you put your right hand around the boundary, you get the direction of your normal. Okay. So let me try this. Okay. Reflux is due to an area increment, assuming you have a constant magnetic field through that area, you just multiply the magnetic field. It's B times A times cosine theta. Magnetic field times area times cosine of theta. And this is the field component normal to the surface times the area. If the field is negative BK and this is in the XY plane, then what you would get here, cosine of theta would be -1. Theta being the angle between the normal vector and BK. We can write this as a vector equation. We regard this area as a vector, magnitude equal to the area, the vector being the north. And it's a dot product. Then you can verify that's exactly what this is. Okay. Right, the small, but it's the biggest thing we've talked about yet. And if this loop is rotating about the X or the Y axis, that will say is write this down. Such a theta equals omega t. When we get that specific. I wasn't planning to talk about this in this chapter, but I think it's beneficial to see it. If 5B is a function of t, then get an EMF. Now, we've already seen that. We've changed magnetic fields and fluxes with the Helmholtz coil and the rotating magnet. You remember all that? Okay. In that case, B was changing, the loop wasn't rotating. Okay. Well, same effect either way. So 5B of t is a function of t. That EMF is just the derivative of the flux. So you rotate a loop in a magnetic field, or rotate a magnetic field around a loop, you get an EMF, and we've been using that in lab for over a month. We've measured it. I haven't told you what the rule is. It's a rate of change of the flux. You rotate the magnet inside the Helmholtz coil, and the flux is changing. I talked about that, waving the hands, but I didn't write it down. Takes the magnetic field of that magnet, which is on the order of 100 to the Tesla, something like that, times the area of the magnet. You get how much flux is changing, because flux changes due to the orientation of the magnet. Okay. Magnet is perpendicular to the loop. You get a lot of flux. Magnet is parallel to the loop. Field lines don't cut the surface. Okay. They don't cut the area. So that's real important. And actually, I think maybe we do talk about flux in the text. So there it is. I think I said a little more than necessary for this chapter, because I don't think this chapter addresses a change in flux. Maybe they do. I'm going to take another quick look. Okay, now imagine I throw this and there's no gravity and no air. In which case, I'm going to have to hold my breath. But okay, we imagine it's positively charged with an upward magnetic field. Make it simple. Then QV is in this direction, and B is in this direction. So my force is in this direction, perpendicular to QV and perpendicular to V. So it's always got to be perpendicular to that. Okay. Well, that's going to change direction. It's going to go this way. Now it's going in this direction. QV cross B is still perpendicular to its path. And that's going to continue, and the thing's going to go on its surface. Assuming that the net force is just the magnetic field. So okay, so assume that your magnetic field is VK, V equals VI. F would be QVB and I cross K negative J, right? So through B. And magnetic field is coming out of the that's how we depict the field coming out of the plane. Imagine an arrow going through a piece of paper. If it goes into the paper, it leaves a little hole. On the other side of the paper pulls out. Okay, so I believe that's convention. I never looked much. I've got it backwards. Well, I'll get it straight. Okay, there we have this. Then the force is this guy. At this point, well, that's going to cause the deflection, so the thing is going to then later be in, let's say, this direction. And at this point, the force is still going to be perpendicular. So your velocity here is right out that would be dxi plus vyj. Okay. Then that is magnetic force. So if we have this, if that net is F, the magnetic force is perpendicular to the path, so it has no effect on the speed. Get here. There's been no effect on the speed at any point because no matter where it is, it's not experiencing upward or downward force, only in the plane and only perpendicular to this motion. The Vx squared plus Vy squared always equal to D. Okay, well, I get another force here, and that changes the direction a little more. And you get another force here. Okay. And what's going to happen is, we do it down to the center here. These forces are all pointing toward the center. And F is, get the whole word in there, but it's centrifugal. And F equals mv squared over r applied to r. Multiply both sides by r, divide by l. There's your radius of curvature. Meaning, if we know the charge, the radius of curvature of the path, we find the mass. Now, it turns out that we can use a Millikan experiment to determine the charge of the electron. Then we put an electron beam in a known magnetic field and we get mass. Okay. Pretty neat. That was measured near the turn of the century before the one they just turned 23 years ago. Okay. About 120 years. 125, maybe 1898. The grandmother of my great aunt was born in 1990. So I might be thinking about it for different reasons. Okay. But it was around that time. Okay. Well, that covers a whole lot of what you're going to see in the chapter. I recommend you get started in the assignment. I know many of you have a strong tendency, some of you at least have a strong tendency to wait a last minute, get these assignments. I'll try to keep it all possible. Spread it out. Okay. Just, you learn better, you process it better and retain it better, but do whatever works.